After studying this module, you shall be able to know about vacuum metal deposition method, the history and theory of vacuum metal deposition method, and the use of vacuum metal deposition technique in development of latent fingerprints. Introduction to vacuum metal deposition method. VMD or vacuum metal deposition is an effective sensitive technique used in the development of latent fingerprints. It is a similar concept to the cyanoacrylate fuming method but substitutes metal vapor for cyanoacrylate vapors. The question surface is placed in a chamber from which the air is evacuated. This chamber also contains small pieces of gold and zinc that can be heated chemically until they vaporize. The specimen is exposed first to gold vapors and then to zinc vapors. The metallic vapors or the metal vapors adhere selectively to fingerprint residues, revealing latent fingerprints or latent prints as the metal plated traces on a pristine substrate. As this technique covers the substrate and not the latent fingerprint, it does not hinder with the sample collection required for the DNA analysis. VMD or vacuum metal deposition can be employed to develop grab marks present on clothing that help in the collection of DNA. The range of exhibits that have been successfully treated using the VMD technique or the vacuum metal deposition technique is extensive and includes plastic bags and packaging, glass and plastic bottles, firearms, glossy card, photographic paper and magazine covers, clean leather items including handbags and shoes, adhesive tapes, that is the non-sticky side of the tape. Because VMD requires expensive equipment and material, its use is limited to well-equipped and well-funded forensic labs. Now students, let us move on to the history of this particular technique. Vacuum metal deposition is a long-established industrial technique for the application of metal coatings to components such as glass mirrors. In the year 1964, Professor S. Tolansky, working on the manufacture of interference filters at the Royal Holloway College of the University of London, noted that the deposition of silver in a vacuum system developed accidentally deposited latent fingerprints on glass optical components very beautifully. An investigation into the process as a fingerprint development technique was proposed by the Home Office by Professor Tolansky. However, this was not pursued at the time by the Home Office because other techniques for the development of fingerprint or fingerprint detection on glass were considered cheaper, easier to use and sufficiently effective. In 1968, it was reported by French workers that the VMD technique or this vacuum metal deposition technique from a mixture of zinc, antimony and copper powder was capable of developing the latent fingerprints on paper. As a consequence of this paper, the interest in the technique was revived in UK and Tolansky initiated a research program to investigate the optimum conditions and the potential applications for VMD. The research program initiated by Tolansky investigated the deposition characteristics of a range of metals on paper substrates, identifying the single metals and metal combinations giving the optimum print development. Research was also carried out into the ability of the technique to detect latent fingerprints on fabrics. These experiments showed that although some print development was obtained by the use of single metals, in general, the best results were obtained by the use of a combination of metals, typically gold or silver, followed by cadmium or zinc. The gold or zinc combination is currently used operationally. The potential of VMD to develop fingerprints on fabrics was further explored by the Atomic Weapons Research Establishment, or AWRE. The work looked at identifying the best metal combinations for developing prints, transfer of both the latent and the developed marks onto the photographic paper, and the effect of humidity on it. The researchers considered the effect of different washing and wearing conditions on print survival and expanded the study to look at the synthetic fabrics. It was considered that the chances of fingerprints surviving on washed and worn out fabrics under field condition were small but finite. In the mid-1970s, the increasing of low-density polyethylene, or LDPE, carrier bags in a variety of crimes. A program of work evaluating the various metal combinations on a variety of plastics and rubbers was set up, and considerable success achieved using the gold, followed by cadmium on polythene and most plastics, with the notable exception of plasticized PVC. This and all the early experimental work was carried out on small scale equipment with 12-inch bell jar coaters. Silver cadmium combinations gave slightly poorer results than the gold cadmium, with copper cadmium less good. Gold followed by zinc deposition was known to give similar results to gold cadmium, although deposition of zinc is slower and more difficult. The decision was made to switch to gold zinc for all operational police systems, as the maximum exposure limits for zinc were many times higher and there was no likelihood of being exceeded in operational use. In particular, the VMD was shown experimentally and operationally to develop fingerprints that had been exposed to extended water immersion, something that no other technique at that time, that is late 1970s and early of 1980s, could cope with. Now we will study about the theory behind the vacuum metal deposition technique. The technique of vacuum metal deposition method for fingerprints is based on the fact that the metal combinations are postulated to work well due to the condensation characteristics of zinc and cadmium. These metals will not condense on grease such as that found in the fingerprint residues, even when these substrates are only present as a monolayer. However, zinc will deposit on small nuclei of metal, and this is the reason that gold or silver deposition is carried out first. Gold and silver can be deposited over the entire surface and they begin to form nuclei, the morphology of which depends on the nature of the surface you have taken. That is, also the surface characteristics are being considered, such as the surface energy, the chemical species present on it. They are being deposited on. The resultant gold coating is very thin, that is several nanometers only, and is discontinuous. However, in the regions coated with the fatty residues of the latent fingerprint, the gold diffuses into the fat, and hence there are no gold nuclei close to that particular surface. As a consequence, when zinc is subsequently deposited, it will condense on the regions of gold nuclei, that is the background substrate, but not on the regions of the fatty deposit, that is the fingerprint ridges or the fingerprint residues. Tests carried out to determine which components of the latent fingerprints were most likely to be responsible for inhibiting the metal deposition identified several substances, including the stearic acid, palmitic acid, cholesterol oleate, glycerol trioleate, and amino acids L-arginine monohydrochloride, L-leucine, and DL-threonine. Most of these substances are non-water soluble or long chain fats or acids with low vapor pressure, which determines their stability and non-migration over the surface during the process of VMT. These findings were in accordance with the observations that had been made earlier to that of the VMD and which was capable of developing prints on substrates exposed to wet environments, many of these substances being insoluble in water. It is now recognized that the gold or zinc VMD process does not work well or at all on substrates that are heavily plasticized. Example, the cling film, plasticized substrates, dispersed gold nuclei, that is a small, densely packed gold nuclei, thick zinc deposit on large nuclei, thinner zinc deposit on small nuclei, dried fingerprint residues and PVC, or the surface release films on contamination. This is attributed to the fact that gold nuclei diffuses into the surface layer of the substrate as well as on the fingerprint deposits, with the result that there are no nuclei on the surface of zinc to deposit on. Now we will study about the role of gold and zinc in this particular technique, that is the vacuum metal deposition method or technique. The role of gold in the VMT process is to act as the primer for subsequent zinc deposition. Gold is not selective in that it will deposit across the entire surface of the exhibit, but the size and dispersion of the gold nuclei formed will be determined by the nature of the surface, that is the chemistry, roughness, etc. As there is usually a sufficient difference between the nuclei formed in the regions of the fingerprint ridges and the background for the print to be delineated during the subsequent zinc deposition, gold is also used as the initial deposition metal because it is inert and does not react with the fingerprint residues or the atmospheric pollutants. The low deposition pressure is used so that gold can be deposited directly onto the surface without colliding with a significant number of molecules in the chamber, giving an even coating. The role of zinc in the process is to delineate the fingerprint, primarily by the difference between the growth rate of zinc on the fingerprint ridges or the residues and by the growth rate on the background also. Zinc is highly effective for this purpose because it easily re-evaporates from the surface unless there is a suitable nucleation site present. Thus, the gold nuclei formed controls the way in which the zinc layers subsequently form. The evaporation pressure used for zinc is higher than that of the gold, and this will allow the user more control over the zinc deposition process. Allowing more air into the chamber makes the deposition of zinc more uniform across the area of the exhibit. It was thought that the additional air molecules present in the chamber would reduce the kinetic energy of zinc atoms, and as they reach the surface and they could increase development rate, but this has never been proven. Now we will study about the VMD instrumentation and its working. A vacuum metal deposition system consists of a vacuum chamber capable of being pumped down to higher levels of vacuum. Then next is filaments for deposition of gold and zinc, and a viewing window so that the deposition of zinc can be monitored. The chamber may also contain a cold finger chilled to low temperature so as to aid the condensation of contaminants and to reduce the pump down times. Articles to be coated are attached to the perimeter of the vacuum chamber above the coating filaments. The filaments used for deposition of gold and zinc are typically formed from thin sheets of molybdenum. The gold filament usually consists of a shallow dimple in a thin strip of molybdenum. This is because the quantity of gold used is very small, that is approximately 2 to 3 milligrams, and it is important that all the gold reaches the substrate. If deeper containers are used, shadowing may occur and not all regions of the article may be coated. Gold deposition takes place when the chamber has reached a pressure of 3 into 10 to the power minus 4 millibars or lower, and the current to the filament is increased until the filament reaches a yellow or white heat zone. Deposition of the gold should be complete within 10 seconds, but if any residue is observed on the filament as a current is reduced, the temperature should be increased again until all the gold has been evaporated. Once the gold deposition is complete, the pressure in the chamber is again increased to approximately 5 into 10 to the power minus 4 millibars, and the current to the zinc deposition filament is turned on. The reason for increasing the pressure in the chamber is to increase the uniformity of the coating produced. The zinc deposition filaments are larger and significantly deeper than the gold filament, and the quantity of zinc added is larger, that is typically 1 gram per run. The zinc used is in the form of foil, shot or powder. For zinc deposition, the current is increased until the filament glows a cherry red or dull orange color. Once this occurs, the operator should observe the deposition process through the viewing window, ceasing deposition as soon as marks becomes visible on the substrate. After zinc deposition, the gold filament should be briefly heated to yellow or white heat so as to burn off any zinc contamination. This is a great variability in the speed at which the different substrates coat, and it may take over 10 minutes to obtain a suitable coating on some types of material. In some cases, it may be necessary to carry out a simple deposition or multiple deposition run in order to obtain the satisfactory result or to develop all the marks present. The presence of surface contamination, release agents or plasticizers may mean that it is not possible to obtain a zinc coating at all, and in these circumstances the deposition of 30 milligram of silver using the same deposition conditions or the technique for gold may yield additional marks also. Now we would be studying about the VMD in detection of latent fingerprints. The vacuum metal deposition technique initially was adopted as an operational technique for the detection of latent fingerprints on thin polyethylene items such as carrier bags and wrappings, and was shown to be superior to other processes developed subsequent to the initial comparison trials. Although the technique had originally been developed with the intention of being used to detect prints or the latent prints on fabrics, no identifiable prints were successfully obtained in operational trials, and VMD is not currently recommended for the operational use on this substrate. VMD has now been used operationally for many years and has been shown to be an effective technique for a wider range of materials than polyethylene. It is evident that there is much overlap between the types of articles that can be treated with VMD and those that are treated using cyanoacrylate fuming. In many cases, the deciding factor as to which technique is to be used is whether the article has been wetted, because VMD remains effective on wetted items, whereas cyanoacrylate fuming does not. In practice, it is possible to use the two processes in sequence also, and more marks may be deleted in this way because the two processes work on different fingerprint constituents. Metal evaporation of gold, zinc, silver, sterling silver, copper, tin, aluminium and other metals makes a noticeable difference in developing the latent prints when the substrate has been processed with the correct metal. When evidence is not processed with the correct metal, the latent prints may appear to be faint or invisible. It is essential to test the substrate with all the metals in order to get the best results or the best prints. It is best practice to keep a log of the substrate types with the compatible metals that will provide a reliable result when you are carrying out this particular technique. As for any type of evidence that is chemically processed for latent prints, there are tests done to be sure so as that the process is the best method. Several other materials have been investigated in the VMD process, including the metal combination, single metals and organic materials. Initially, the gold or cadmium combination was selected as the optimum process, with cadmium giving better results than zinc when used as the second metal. It is also easier to produce coatings using cadmium. But however, cadmium is very toxic and its use is no longer recommended on health and safety grounds. Silver can be used in place of gold as the initial deposition metal, and limited evidence suggests that it would have little effect on the effectiveness of the whole process. However, silver is more likely to interact with the fingerprint constituents or the atmospheric contaminants, and for these reasons the more inert gold is the preferred one. But when silver is used in case of gold or zinc for the plasticized materials and for materials with surface layers of contaminant, as has been stated in the Philipson and Blee 2007 papers, this silver VMD technique is thought to work because silver, like gold, deposits uniformly across the surface. The nuclei formed vary in size and distribution between the fingerprint ridges and the background, giving a difference in color between the two regions, that is the fingerprint and that of the background. It is thought that the copper works in a similar way, but the resultant color of the film formed is different. Let us summarize this module. VMD or vacuum metal deposition is an effective sensitive technique used in the development of latent fingerprints. We have also studied that the range of exhibits that has been successfully treated using the VMD is extensive and include plastic bags and packaging, glass and plastic bottles, firearms, glossy card, photographic paper and magazine covers, clean leather items including handbags and shoes, adhesive tapes, that is the non-sticky side of tape. The technique of vacuum metal deposition method for fingerprint is based on the fact that the metal combinations are postulated to work well, that is due to the condensation characteristics of zinc and as well as cadmium. The role of gold in the VMD process is to act as the primer for subsequent zinc deposition. The role of zinc in this process is to delineate the fingerprint primarily by the difference between the growth rate of zinc on the fingerprint ridges and the growth rate on the background part. A vacuum metal deposition system consists of a vacuum chamber capable of being pumped down to high levels of vacuum, filaments for deposition of gold and zinc, and a viewing window so that the deposition of zinc can be monitored. VMD has now been used operationally for many years and has been shown to be an effective technique for a wider range of materials than polyethylene. Several other materials have been investigated in the VMD technique or process, including the metal combinations, single metals and organic materials.